Hi scholars, I hope that you and your family and loved ones are doing well. We at SEO are thinking about you every day, we care about you, and we're sending our best wishes. So usually in an SEO math class, we all rely heavily on your knowledge, your thoughts, and the ideas that you bring into the classroom. And there are many opportunities for you to talk with your classmates about an idea or to come to the board, to share what you're thinking, to ask questions, and just in general to solve problems together. And so although much of these activities aren't possible when you're watching a video, I still encourage you to try to watch this video as if you were in a classroom actively. And so what this means is to take out your workbook or a notebook while we go through the lesson together and take notes in it, just as if you were in a classroom. Feel free to pause, rewind, and watch parts of the video a second time if you're confused. And make a note of things that you're still confused about after this lesson so that you can ask your instructor. All right, sounds good. So let's get to it. Two trees are growing in a forest. Tree A was 2 feet tall last year and is 6 feet tall this year. And tree B was 10 feet tall last year and 14 feet tall this year. So we're comparing tree A and tree B. And the question we want to answer is, which tree grew more? So take a second and come up with an answer for yourself. Okay, and so there's really two ways of thinking about this. So one way is to think about, well, how much did they grow? Well, tree A grew, right, 4 feet, right? And tree B, well, tree B also grew 4 feet. And so one way that we can think about it, we can call this an additive model, because we're really just asking how much did each tree grow in absolute terms, right? Well, A and B, right, each grew by 4 feet. So the question, which tree grew more? They grew the same amount, right? Each grew by 4 feet. Okay. Now, is there another way to think about this question? And there is, right? So another way to think about it is to ask yourself, which tree grew the most relative to its starting point, relative to where it was. Okay. So tree A started at 2 feet. And then it grew, well, how many times its original height did it grow to get to 6 feet, right? Well, it grew 3 times its original height, right? Because 2 times 3 is 6. Tree B, it was already at 10 feet, and it grew to 14 feet, right? Well, we can imagine if it had doubled in size, right? If it had increased by its same amount again, it would be up at 20 feet. So in fact, this is less than doubling its size. It ends up being multiplying by 1.4. You could also multiply by 7/5 in order to get to, right, our 14 feet. And so in this case, if we want to think about this in terms of a multiplicative model, in this case, we can say that tree A, right, grew 3 times its original size, right? And so that's the important piece, right? We're comparing the growth to its original size using multiplication, right? How many times bigger is it? And tree B grew, what did we say, 1.4 times its original size. And so thinking about the multiplicative model, we can say which tree grew more? Well, tree A grew more, right? Because it tripled in size, whereas tree B didn't even double. It was a little less than doubling in size. Okay, let's keep going. So let's take another look at this idea of the difference between additive and multiplicative growth, just like in the tree example. And we're going to see that the multiplicative model, it's really sort of a foundation for proportions. Okay, so in the picture to the right, we're measuring a 3-foot bar with a 1-foot ruler. So again, we talked in the last lesson about a quotative or a measuring model. This is one way to interpret fractions, right? And we can write this as 3/1. Okay, that's easy, right? And we could say it would take 3 rulers to measure this entire bar, right? So there's 1 ruler, there's 2, there's 3. So pretty simple, right? And so that's why 3 is equal to 3/1, right? Length of 3 measured with a ruler of 1. Okay, so let's take a second and draw a picture of what it would look like if we just added. So here we're going to take a look at this this additive model. We added 2 feet to each of the bar and the ruler. Okay. Well, it used to be 3 feet, the bar. So instead of 3 feet now, it's going to be 3 plus 2 is 5 feet, right? There's the original 3 feet, let's say, and we just added 2 feet. So this right here is going to be our bar, our 5-foot bar, and if we add 2 feet to the ruler, I'll just use a different color just so we can see, then it's going to be 3 feet, right? The ruler is going to be 3 feet, and here it is, right? And so our question is, how many rulers would it take to measure 5 feet, right? Our bar. And the answer is, well, we can see it's not really important how many it takes, but the question really is, did your answer change, right? If we just added a little bit to the ruler and a little bit to the ruler and a little bit to the bar. And the answer is, yeah, it did change, right? Because our answer here was it would take 3 rulers, right? Well, here, if I had 3 of my 3-foot rulers, right? If I did, oh my goodness, I'd be up to like 9 feet already, right? This is what 3 rulers would look like. So in fact, it would take fewer than 3 rulers. In fact, it would take, right, even less than 2 rulers. It would take, in fact, 5/3 of our new ruler, say of the ruler. And so our answer did in fact change, okay? So numerically, algebraically, what does this mean, right? We're really asking the question, can I say that if I add a little bit, right, to the numerator and a little bit to the denominator in a fraction, does that equal the original fraction, right? And the answer is no, it does not, okay? So even though it looks like, well, look, I have a 3 here and a 1 here, and here's my 3 and my 1, and right, I know that 2 is equal to 2, right? So it looks like they could maybe be equal to each other. They are not equal to each other, right? And so algebraically, notice here I'm just taking, instead of writing 3, I'm just using a variable a to say it could be any number, right? Same thing with 1. The 1 here is the variable b, and the 2 here is our variable x. And so we could ask algebraically, is this true? Does a plus x over b plus x, does that actually equal a over b? And the answer is, right, we just did it. No, it doesn't, okay? So in general, this is not true. It's true in the case when x equals 0, right? But then you're adding 0, it doesn't really change anything. Okay, let's keep going. So that was really an example of the additive model. Let's look at the multiplicative model. So where our next example says, let's draw a picture of what it would look like if you made the original bar 2 times as long. Instead of, right, adding 2 feet to it, but you made it 2 times as long, right? Times is multiplication. And you made the original ruler 2 times as long. Okay, well, originally we had a length of 3, right? So instead of a length of 3, let's make it 2 times as long. So here's our new ruler, or our new length, which is 6 feet, right? Because it was 3 and we multiplied it by 2. And our ruler, originally it was 1 foot, so let's also multiply that by 2. And so our new ruler is going to be 2 feet. Okay, so let's just take a look just to make sure that we're doing this right? Originally, right, we had our, we were right up here. We had a 3-foot length and a 1-foot ruler. All we did is we multiplied the length by 2 and the ruler by 2. Great, and so we have 6 and 2. And we said originally that it took 3 of those rulers, right, to measure that length. And is that the same case here? Well, let's see. How many 2 feet would it take to measure 6 feet? Well, 1, 2, 3. So it would take 3 rulers, just like what we had before. Did our answer change? The answer is, oh no, our answer did not change. It did not change. And so numerically, right, all we did was we multiplied the numerator and denominator by the same amount, right? And the question is, does 3 times 2 over 1 times 2, does that actually equal to 3 over 1? And the answer is yes, it does, right? This is a proportion right here. And so algebraically, we can say that unlike when you add, right, up here we said when you just add the same number to the numerator and denominator, it doesn't equal your original fraction. But here in this case, we say, does it equal it? Well, yes, it does actually, right? So this right here is sort of a key to proportions. The idea is that although the numerator and the denominator may change, they're changing sort of by the same amount, by the same magnitude, multiplicatively, right? That's really the big idea. All right, let's keep going. So let's quickly go over some definitions. Okay, so a ratio is a comparison of one measurement in relation to another, and we can write ratios as fractions. So for example, if you remember our think, pair, share, one way that we could say that tree A, right, it was 2 feet and it went to 6 feet, right? We could say how many times bigger did it grow, right, during that year, right? We could write that as this ratio, right, 6 feet over 2 feet, where we're comparing the final height to the original height, to the starting point. So again, everything is relative to the starting point. And this is an example of a ratio. It's a comparison of one measurement in relation to another, feet to feet, right? And so we said, oh, this is 3, and that means that it grew 3 times as much, right? A rate is a ratio of two measurements that have different units. And so I'm sure you could think of an example of a rate. One example of a rate is velocity or speed, right? When I say I can run 10 feet in 2 seconds, for example, right? This is a rate. I could say, how much does milk cost? It costs $4.50 per 1 gallon. This is another example of a rate. So again, it's a ratio, so we can write it as a fraction, but we're talking about two measurements with different units. So dollars and gallons, for example, or feet and seconds. And finally, this is sort of the key to our lesson today, a proportion. So a proportion is an equation that indicates that two ratios are equal. So for example, I could write the proportion 3/5 equals 6/10. And this is a true equation. It's an equation that says that this ratio and this ratio are equal. And I could also write, for example, I could say 12 meters per second per 1 second, right? Maybe a car is driving at 12 meters per second. I could say that's the same thing as saying that a car is driving 60 meters in 5 seconds, right? If the car is moving at an average speed. So this is another example of a proportion. All right, let's keep going. So let's take a look at proportions within the context of a word problem. So a manager at Chipotle is worried about the quality of burritos being made at her store. So, okay, she selects 2 burritos at random for inspection out of every 9 burritos made. So we can already set up a ratio here, and the ratio is going to be the number of inspected, right, over the number made of burritos, right? And so we already say that she selects for every 9 burritos that are made, she's selecting 2 of them. And we're going to use this ratio as a starting point to set up a proportion. So at this rate, how many burritos will she inspect if 27 burritos are made? Okay, so we have 27 burritos are made, and this how many, right? Well, this is asking us to find this number, so we can call this an x, right? Our unknown that we can solve for. So our question is, at this rate, well, if 27 burritos are made, right, how many will she inspect? Again, we're keeping, just to make this clear, right? Let's say if this is my 2 burritos at random, and this is my how many, my x right here. This is my 2 here, and this is my x. And over here, we're saying out of every 9 burritos made, and 27 burritos are made, so this is the number that's burritos being made. It's always in the denominator in these fractions. So this all works out. We're matching the units in the numerator and the denominator when we're making this proportion. Okay, so we can solve this, solve for x, right, by cross-multiplying. I just want to also just show you a quick way that we could do it is you can also reason and you can say, well, remember we were saying that the way that proportions work is that the numerators and denominators grow together multiplicatively, right? And so I could say, well, if I have 9, what do I have to multiply it by to get to 27? Oh, I have to multiply by 3, right? And so I can use that same idea here and multiply by 3 here to get my answer, my final answer of x equals 6. And you would get the exact same answer if you cross-multiplied. So let's just take a look at that really quickly. If I cross-multiplied, I would get 2 times 27 is equal to 9 times x. 2 times 27 is 54 equals 9x, and we can divide both sides by 9 and get that x does in fact equal 6, right? So these are two different ways to sort of get the answer. So the answer is she will inspect 6 burritos out of those 27 that are made. Okay, so let's take a closer look at this idea of cross-multiplying to verify that a proportion is indeed correct. So we know that this is an algorithm that we can use to solve proportions. So for example, this is the exact same one we just had. We had 2/9 equals x over 27, and we cross-multiplied, and we ended up with an equation that we could use to solve for x. So why does this algorithm work? So take a second to think about that, and see if you can sort of reason through why this cross-multiplying algorithm might work. Okay. So let's start with our original proportion, which is 2 over 9 equals x over 27. And if we remember when we first started talking about how we could compare fractions, like which one is bigger, right, relative magnitudes, right, we said that we got to make sure that the denominators are the same, right? We want to have a common denominator, and then we can sort of compare the numerators, right? And so this is really the way that we can sort of reason about fractions. Okay, well, there are easier ways to find like a least common denominator, but let's just say in general, well, here I have a 9 and here I have a 27, okay? Well, if I had a 27 here, right? So I can multiply the top and the bottom here by 27 over 27, right? If I had that 27 here, then I would have that common denominator of 27. And on the other side, I have a 27, but I have a 9 over here, right? So let's multiply that by 9. Again, we got to multiply the top and the bottom by the same thing. And now if we just look at the denominators, so that this denominator is 27 times 9, and this denominator is 27 times 9, and oh, they're the same, right? So since they're the same, I can sort of ignore them, and I can just look at the numerators. And if I just look at the numerators and rewrite the numerators, I have 27 times 2 is equal to x times 9, right? Just the numerators right here. I'm just rewriting that, and I'll be darned if that is not the same result that you get with one step in cross-multiplying. So this algorithm, it's a nice sort of shortcut, but it's really based on this idea of being able to compare the numerators of fractions so long as the denominators of these fractions are the same. Okay, so that's sort of the reasoning behind why this algorithm works. All right, let's do one more example. Example number 4, Sid jogs 3 blocks to catch the bus, and it takes him 89 seconds. So if he jogs at the same rate, about how many minutes would it take him to jog 25 blocks? So we have a couple things going on here. So one thing is we're being asked to, we see this word about. So about how many minutes? That's saying it's sort of like an estimation. So if I'm looking at this problem and I see that it takes him 89 seconds and I'm being asked to estimate, I can say, yeah, it takes him about, 89 is about 90 seconds. And that's really helpful because 90 seconds, right, we can say how many minutes is 90 seconds? Yeah, it's about 3/2 of a minute, otherwise known as 1.5 minutes, right? So once we have that estimation, 89 is about 90 seconds, we also want to take a look at the units that are being used. So here we're being given his rate in blocks per second. And here we're given his rate in, or we're being asked to calculate his rate in blocks per minute. Okay, so at some point in this solution, we're going to have to take into account seconds and minutes. And we know, of course, that in 1 minute, there are 60 seconds. Okay, so I'm just going to write that over here. So let's solve this problem 2 different ways. Okay, so the first way is let's set up a proportion where we're going to use minutes as our time. So we have a rate of, we know that he jogs 3 blocks. We're going to set up 2 proportions using this blocks per minute This is sort of our units. And so we know that he does 3 blocks in how many minutes? Well, we said 89 seconds was around 90 seconds, and 90 seconds is about 3/2 of a minute. Let's just keep it as a fraction. So our ratio over here, our rate, is 3 blocks over 3/2 of a minute. Okay, so it's a fraction over a fraction, but it's okay, we can deal with that. And we're being asked if he jogs 25 blocks, so blocks again are on our numerator side, right? So 25 blocks, how many minutes would it take him? So this is our unknown, right? So this is our x minutes, okay? So we have, just to verify, we've set this proportion up correctly, blocks per minute. We are having blocks per minute. This is what we're given, and we want to find out this value of x, and again we've set it up with blocks per minute, so we're all set here. And we can cross multiply and solve. It does get a little ugly. Let's just do it really quickly, but it's nothing we can't handle. So this is our 3x is going to equal to 25 times 3/2. 3x is going to equal to 75 over 2, and we can divide by 6, so we get that x is equal to 75 over 6, and we can simplify that as around 25 over 2, which is about 12.5 minutes. So I could say 12.5 minutes. Okay, so this is one way that we can answer this question. It would take him about 12.5 minutes to jog 25 blocks. So let's look at this problem in a slightly different way that involves reasoning about his rate. So here's another solution strategy. So we know that Sid can jog 3 blocks in about 90 seconds. Okay, so I have 3 blocks in 90 seconds. Okay. One question we could ask ourselves is about how long does it take him, right, to jog 1 block? Right? How many seconds? And well, we could cross multiply and etc. That's totally fine, but really, right, to go from 3 to 1, I'm really multiplying by, let's put it in a different color, this is multiplying by 1/3, right? Because 1 is 1/3 of 3. And so if I want to go from 90 seconds over here, I want to be multiplying by the same amount, by 1/3. So what's 1/3 of 90 seconds? Well, the answer is that's 30 seconds, right? You would have gotten the same answer if you cross multiplied, but this is really nice because now we know how long it takes him, how many seconds it takes him to go 1 block. It takes him about 30 seconds. Okay, we can rewrite that using minutes. I can say that his rate per block, every block it takes him about, well, 30 seconds is half of a minute, right? Okay, so now let's look at our question. Our question again is asking us how many minutes would it take him to jog 25 blocks? So let's use this 1 block every half a minute, right? So I can set this up over here, 1 block every half of a minute, right? How long would it take him to go 25 blocks? And that's nothing more than, right? If we want to reason proportionally, we're multiplying the numerator by 25, so we got to do the same thing over here. Multiply this by 25 to get our value of x over here. And what is 1/2 times 25? Well, I'm just going to put it over here. Sorry, we're running out of space. 1/2 times 25 is going to get you 25 over 2, otherwise known as 12.5 minutes, right? We get you the exact same answer. So this is one way of reasoning about it, this problem, by breaking it down into sort of a more manageable unit rate, right? 1 block every half of a minute, for example. I hope all is well, and stay safe.